In this video, we will watch as a round ball of diameter 10 centimeters and mass 35 grams moves in a straight line in the same direction and at the same speed. The primary goal of the exercise was to observe the motion of the ball and to construct a model to predict this motion. After comparing the model with the experimental results, it was discovered that the model accurately predicted the motion of the ball according to Newton's second law of motion. Now, let's look at Newton's second law of motion. It states simply that acceleration equals force divided by mass. Now, if we were to simplify acceleration to Vf minus Vi divided by delta t and solve for just Vf, we would have the following expression, where Vi is the velocity at the start point, Vf is the velocity at the end point, and delta t is the interval of time in which we are observing the motion. The force in this case is the total net force acting on the object in motion, while m is the mass of the object. Now, let's take a look at the observations that were made about the motion of the ball. From the position versus time graph, we can see that the graph is fairly linear, indicating constant velocity. The ball is moving in the positive x-axis because we chose to orient the axis that way. We could have easily oriented the axis so the ball moved in the negative x direction or even in any of the y-axis directions. The only thing that would change is that the graph would be moving in the opposite direction for the negative x and y axis. However, the velocity would remain constant and its magnitude would be the same. Now, if we go back and look at Newton's law of motion, we see that constant velocity means that both Vi and Vf must be equal. This only happens if the second part of this equation is 0, which can only happen if the net force on the object is 0. Although we do not know the magnitude of the total forces pushing or pulling on the object, we do know that total net force is 0, which is all we need to predict the object's motion. Let's observe the position versus time chart. As we can see, at t equals 0 seconds, which is the initial position, or the initial time, the initial position of the ball is 0.001 meters on the positive x-axis. We can also see that the time of last observation is 0.767 seconds. To calculate the initial velocity of the ball, we can take the first measured position of 0.001 and subtract it from the second measured position of 0.009 and then divide by the change in time, which is 0.033 seconds. If we do this, we get an initial velocity of 0.2424 meters per second. Now let's look at the code used to construct the computer model for the motion we are observing. First, we have to specify the initial conditions of the position and the velocity. The initial position is indicated by the vector 0.001, 0, 0, while the initial velocity is indicated by the vector 0.2424, 0, 0. Both the y and z portions of these vectors are 0 because the ball is only moving in the positive x direction. Next, we must specify a delta t that is very small, such as 0.01 seconds, in order to obtain accurate predictions of our model. We can see that the net force is set equal to 0, 0, 0, and according to Newton's second law, the final velocity and the initial velocity should be the same because the second part of the expression is always 0. Next, the position of the ball is calculated every 0.01 seconds by taking the previous position and adding it to the velocity of the ball times delta t, which is 0.01 seconds. This is done until the time is 0.767 seconds, which is the time of our last observation. Now, if we run the program, we should be able to see our computer model. As we can see, the ball starts at the origin and moves towards the positive x-axis. The position versus time graph shows a straight line, indicating constant velocity. Now let's compare our prediction model to our actual experimental data. The red line indicates the model that we created using the code, while the blue dots represents the data that we collected from the motion of the ball. As can be seen, the model predicts the position of the ball well at the beginning and at the end of the observation. However, in the middle of the observation, the position of the ball is slightly above the expected position. This could have resulted because the ball may have still been speeding up at this time while the observations were made. Nonetheless, both of these graphs show that as long as the net force is zero, the velocity of an object will always be constant, and the object will continue to move in the same direction at the same speed until another force acts on it.